in this class, I will tell you about total internal reflection. We have already done refraction. Now, I am taking two different mediums and N1 greater than N2 means this medium is denser than this one. So this may be water, air, maybe glass, air, something like that. And consider a light ray falling on this surface which is separating the two mediums of different refractive indexes. This is normal and when moving from denser to rarer medium, this ray will move away from the normal. So maybe like this. So if this is rarer than this, R will be more than I. The angle of refraction, the ray moves away from the normal. Now what will happen if I increase the value of incidence angle? Let me take it slightly greater than this value. So this R will keep on increasing. Sin I upon sin R, Snell's law, refractive index of second medium with respect to 1, n to 1. Or I can write it denser or rarer. That will be better. This denser and this is rarer. So refractive index of second medium with respect to first, rare with respect to dense. Sin I upon sin R is equal to N2 by N1. So here it will be NR upon ND. So NRD. Okay. So this is to remain constant. So if I am increasing I, sin I will increase. So sin R will also increase because this ratio is to remain constant, Snell's law. So R will increase. Sin R increasing means R will also increase. The value of sin theta increases when theta increases. Okay. So R will increase. So it may happen that at one particular value of incidence angle, R becomes 90 degree. This is R, which is 90, angle of refraction. And this value of incidence angle in denser medium, we call it critical angle. So critical angle is that angle in the denser medium for which the angle of refraction in the rarer medium is 90 degree. Okay. Now if IC is further increased, if I take IC more than this, value of I more than IC. This is I and let I be greater than IC. Then this light ray will not go to the second medium or will not move even parallel to this surface. It will return. And this angle will be equal to this. This will follow the laws of reflection now. So see now, two mediums are involved. Transparent medium, but even then the light ray is not going to the other medium. It's not passing through the other medium. It is coming back. It is returning to the same medium. This phenomena we call total internal reflection. So when a light ray is moving from denser to rare medium and it strikes the surface at an angle more than critical angle. So these two conditions for total internal reflection. You can note down. The light ray must move from denser to rarer medium, and second one, the angle of incidence should be more than critical. If these two conditions are satisfied, the light ray will not go to the other medium, it will return. And we can find out the value of critical angle using Snell's law for this particular condition. Sin IC upon sin 90. It is NR by ND. So sine IC is equal to 1 upon ND with respect to R. Okay. It is NRD or 1 upon NDR. Okay. I can even write it NRD or NDR, right? Refractive index of denser medium with respect to rarer medium, refractive index of rarer medium with respect to denser medium. The refractive index of the medium for which you are calculating is in the numerator, and with respect to which you are calculating, that comes in the denominator. So this is how the angle, critical angle, can be calculated. Depends on the refractive index, and refractive index we have already done on what factors it depends. The value of refractive index will depend on both the mediums, and it will also depend on the wavelength of light. From here we can infer now for which wavelength critical angle will be maximum. Just think, for which wavelength, for which color, red or violet, critical angle is maximum. It will be maximum for minimum value of refractive index, and refractive index is A plus B by lambda square plus C by lambda 4. Red has minimum refractive index, so critical angle will be maximum for red, minimum for violet. It's very important and useful topic and is used in many applications are there. Okay. We shall discuss 3 or 4 applications of total internal reflection. The first one, let me take a prism, maybe of glass. Okay. Light ray falling on this particular surface. Now here the angle of incidence is 0, it will go straight. Angle of incidence 0, so angle of refraction is also 0, going straight. Now it strikes this surface. Now at this surface, what will happen? It may move out, it is air, or it may not. Why it may not? Because this is denser and this is rarer. So whether the light ray will go into this medium or not, it will depend on the value of incidence angle, whether it is more than the critical or less than critical. So how we can draw a normal here, and this is the angle of incidence. Now I am taking all situations. If I is greater than IC, if this angle of incidence is more than critical, then what will happen? Total internal reflection. And in total internal reflection, the light rays will follow the laws of reflection. So the light ray may reflect, it may at an angle of incidence I, it will return at the same. It may be particular case that I is 45, then the angle of reflection will also be 45, not necessarily though, right? So it may return like this. Here I have taken I as 45, so this and this, they are at 90 degree. It will depend on the questions given to you, right? So if I put an object, this is one particular ray, if we keep an object like this. So from here, I have taken this light ray from here. So if this is AB, this is B dash, and this is A dash. So we may get an image using a prism. So not just mirrors, even prisms and transparent mediums can be used to reflect light. We call such type of prism reflecting prisms, and depending on the value of incidence angle, any prism can be used to reflect. Another example. I am just changing the direction of incident ray. And again, assume that the angle of incidence is more than critical. And if I again take that angle of incidence is 45 degree, it will come at 90 degree, and then again 45 it may go. Not always like this, it will always depend on what is the value of incidence angle and what is the value of critical angle. So if it is more than this and angle of incidence 90, then the reflected ray and the incident ray, they will be perpendicular to each other, and it may come like this. Here also it may be used to get images. So if it is A, B, B is coming here, so it is B dash, A dash, B dash, B, sorry, it is A, this is A dash. So this is how we can reflect. Now take another situation. Suppose I is not equal to or more than IC. This I. Now if this I is less than IC, then what will happen? Refraction. It is denser, it is rarer, so the ray will move away from the normal. This is normal, it will move like this. And what if I is equal to IC? It will come like this. The angle of refraction will be 90 degree. This is when I is IC. So depending on the value of I in respect to the critical angle, reflection or refraction will occur. Refraction if the angle of incidence more than critical, and if I is more than critical angle, there will be no refraction and there will be total internal reflection. This was one. I will show you an activity, just observe it properly. Okay. Now, another phenomena that can be explained using total internal reflection is mirage. It is an optical illusion in which on a hot summer day it appears that there is water on the surface. When you are driving and going on a highway and the temperature is high, it appears that there is water on road. I am showing you few pictures. Just see them properly. Okay, what is happening here? On a hot summer day, the air which is in contact with the land surface, that becomes hotter. And when the temperature is high, the refractive index is less. So as we move above the hot land surface, the refractive index is increasing. The air which is in contact with the land surface has lower value of refractive index, while as we move away, the refractive index is more and more. So if we are standing here, okay, and there is some object here. Let me take a tree. Now how the light rays from this tree will reach to your eyes, because now the refractive index of all different layers of air is not same. So I am taking just one or two rays. Suppose one light ray I am taking from this part, and let us take 2-3 layers of air, though the variation is continuous actually. But just to make this explanation easier, I am taking 2-3 layers with different refractive indexes. This one minimum and increasing. So just take one light ray. It is moving from denser to rarer. So it will move away from the normal. Now it is again moving. So again away from the normal. Now in this case, see, angle of incidence to the next layer, is it going on increasing? Here it is less. It is more, it has further increased. Now if this angle, this is denser, this is rarer. If this angle here is more than the critical angle, I can take one more, okay, or it's okay, then it will be reflected. So instead of going here, it will move like this, and then it is moving rarer to dense, so it will move like this. And to our eyes, it appears as if this light ray, instead of coming from A, it's coming from A dash. So actually we see the inverted image of this object. So it can be explained on the basis of total internal reflection and variation in the refractive indexes because of change in temperature. Land surface hotter, as a result refractive index is minimum. As we move above the land surface, the refractive index is increasing, and this variation is continuous. I have taken 2-3 layers, but it's not like that actually. The variation is continuous. Now we can take another activity. This is working of optical fibers. Optical fibers are glass strands, very thin. The thickness is in micrometers, and they work on this principle of total internal reflection. I am telling you how does it work. This is a glass strand. There are two parts of glass. The central part we call it core. This is cladding, core, cladding, and then outermost there is a protective layer, maybe of Teflon. This is glass. This one has a refractive index which is much higher than N2, okay, higher than the refractive index of cladding. So what will happen? If the light ray strikes at an angle, this is dense, this is rare. So it will move out only if the angle of incidence is less than critical, otherwise it will not. So if we make it narrow, so the light ray which is coming most likely to strike at an angle more than critical, because narrower it is, more will be the angle of incidence, because this light ray will almost be straight. In such case what will happen? This will strike and this is. So it is trapped in a way, though it is not a pipe, it's not hollow pipe, it's solid. But even then, a light ray which enters into it, in a way trapped. The thickness is very less, in micrometers. I am showing you one optical fiber, this one. Now see, this is the actual optical fiber, including this is the protective layer. And then inside part, this is the glass strand. You can see it, how thin it is. It is in micrometers, just like here. And another activity I can show you how it works. This is available in the market. Again, these strands, they are very thin, you can see that. And it's not, each strand is not hollow. That you have to keep in mind. It's not so that it is hollow and light is passing through it just like water. It's not like that. It is solid. And how does it work? Okay, this is a light source, and if we keep it here, now you can see. This is how the light is coming out from the other end. So even if I bend it, see, I have bent it, but even then. So it means light traveling through these strands actually bend. It will follow the strand wherever it is. So this way, any signal, optical signal, can travel through an optical fiber. Optical fibers are fastly replacing the cables because they have many more advantages than the cables. In cables, the signal travels in the form of a current, and current involves losses. Further, the frequency of light signals is very, very high in comparison to those signals which we use in cables, radio waves or microwaves. So due to high frequency, we can accommodate more number of users. A particular strand can be used to accommodate 2000 telephone connections. But in cables, the number of users is very less. And further, this is glass. So don't degrade, it doesn't degrade easily. Optical fibers don't degrade. So that's why the life of optical fibers is much more. Quality is better, there are no losses, heat losses are also not there, and radiation losses are also minimized. So this way, the losses are minimized if we are using optical fibers in comparison to the ordinary cables. So these are replacing the cables nowadays. Clarity, number of users, all better than in cables. Okay, so this is all about total internal reflection. In next class, we will take up refraction on curved surface.